this webinar, I think, was received with a lot of excitement. We had almost 100 people sign up, so we're very excited to share this information with you. So I'm going to start off by talking about who we have on video here, who we have as some of the presenters, and some of the information we're going to share with you over the next half hour or so. And we're going to capture a typical engineering challenge that we see quite a bit. And we're going to be talking about how we're solving that engineering challenge using the accelerated computing technology from NVIDIA and Exxact. And then we're going to show you guys what you probably want to see, which is the results of the benchmarking that we've been working on. So we'll start off with a little bit of introductions here. So myself, I'm Jim Shaw, Managing Director of Fastway Engineering. We are an ANSYS channel partner based in Chicago, Illinois. And joining me is Corey Davis. I will say that the majority of the screenshots that you've seen, that you will see today for ANSYS and for Fluent, were all done by Corey. So Corey may be a little quiet today, but I assure you he's put a lot of work in for the webinar today. I'll be doing most of the talking, and I'll hand it over to Himanshu from NVIDIA to do a quick introduction.
Yes, hi everyone. Thanks, Jim. My name is Himanshu Iyer. I lead industry marketing and strategy for the manufacturing industry at NVIDIA.
And my name is Justin Wang. I'm the product marketing specialist at Exxact Corporation, a industry-leading high-performance computing solutions provider.
Awesome. Thank you, guys. Really appreciate you joining us today, and thanks a lot for your partnership and for helping us out over the last few months as we conduct the benchmarking. Well, a lot of you have probably been paying attention around GPU technologies and NVIDIA in particular, and are probably pretty big fans of the computing sort of technology. But we want to provide a solution that is in context. And so the context that we have today is electronics cooling, right? So many of us may be mechanical engineers per se, but everything we do is going to be related in some way to electronics. And so every single industry, of course, has trends towards denser electronics, more IOs, if you will, more power, trying to fit all that into a tighter space. And what that does is that drives up some of the density of the printed circuit boards and electronics, makes them heavier, and increases the thermal load. And so today, what we're going to be doing is we've benchmarked some of the technology from NVIDIA around how do we make a thermal analysis in Ansys Fluent go faster? How do we get more detail? How do we analyze a thermal load? How do we analyze heat transfer? So the physics that we're solving for those hopefully in the audience who are familiar, a technology we call computational fluid dynamics, a family of software technologies have been around for quite some time. And the category of physics, we call it conjugate heat transfer. And that just means that we have a mix of conduction, convection, and radiation. So we're analyzing both solids and fluids. And one of the challenges that we've always had with electronics is what we call sort of the scale problem, right? We've got ICs, traces, small thin parts down at the microscopic level even, maybe at the millimeter size. Those get assembled onto printed circuit boards that could be measured, say, at the centimeter size. They're put into packages, right, into compartments, into mechanical fixtures and cabinets. And ultimately, which is really popular nowadays, a gigantic data center. And those can even be measured in meters in many cases. And so when we're analyzing heat transfer, we have had to pick that scale. Are we going to pick the millimeter scale, the centimeter scale? And because of computing limitations, we've kind of had to stay inside that scale. Well, what that really means is we're developing technology to keep our electronics cool is we end up developing some really high aspect ratio geometry. You are probably familiar if you've been a designer or a fan, if you will, of the electronics technologies, whether consumer or industrial. But we've got a host of different ways of trying to keep our internal circuits cool, finned and pinned, heat sinks, grates, plates, louvers, filters, heat pipes, of course, in some of our laptops. And so as a design engineer, as a modeling engineer, I'm in CAD, I'm in CFD, and trying to create a full fidelity physics model is usually hampered by my computational power. I've got huge patterns of really, really thin parts. That's going to push my CAD program I've got my mesh count, if you're familiar, right, in CFD, that goes up into the millions, if not tens or hundreds of millions. And so we've had all these methods trying to capture the actual physics, trying to capture heat transfer, trying to capture some of the fluid characteristics like the boundary layer, and trying to capture accurate pressure drop, right? We're trying to put fans in, we're trying to keep things cool. And so we've got a whole host of simplifications, right? A necessary error, if you will, that we've had to build into our CFD models. And I'll give you an example of that. Those who have modeled before are probably familiar with what we call the porous media assumption, or Darcy's law. Well, that basically means that we don't have enough computational power to do this filter or this grate or this fin heatsink. And so we model it in CAD as a block, as a simple rectangle. We mesh it very coarsely. But to do that, we have to enter in information that we don't know. What is the pressure drop? What are their inertial losses? We actually make this fancy calculator that CFD is even more complicated. And so for years, we've had to basically introduce more error into our CFD models. We've had to increase the level of effort for pre-processing. We've had to do more testing. The whole point of simulation is to try to reduce the testing load. And we use assumptions like Darcy's law for porous media. We end up having to make a simplified wind tunnel to try to capture pressure losses and viscosity losses and heat transfer coefficients for this filter or this porous media. And so in a way, our efforts for increasing accuracy of modeling and increasing our insight for engineering have been hampered by the hardware limitations that we've had. And so that was then. Of course, we're here today to talk about solutions. And so I'm going to hand it over to Himanshu from NVIDIA to talk about ways that by increasing in the ceiling of your computational power, that we're able to get more insight faster.
Yep. Thank you. Thanks for that background, Jim. So as I mentioned, my name is Himanshu Iyer, and today I want to give you a brief overview of how NVIDIA and Ansys, we are working together for many years now in providing these solutions for designers and engineers to be able to perform fidelity simulations, to be able to perform these simulations faster in order to be able to create optimal products, create better products that you are working on. So let's go to the next slide, Jim. So from the way we see it, accelerated computing, essentially computing with GPUs on the NVIDIA platform, are at a tipping point today. CPU compute has not been scaling over the last few years. It has kind of tapered off. And even currently, there are hundreds of billions of CPU hours that are spent running these large-scale simulations. And as we all know, products in all these industries that Jim mentioned earlier, those products are becoming more complex, right? Because of a lot of different considerations, stress-related, heat-related, electromagnetics related. So these products are becoming more complex, and these simulations, they are not keeping up for that increased level of complexity, right? These could be across, like I mentioned, fluid dynamics or electromagnetics, structural simulations, crash simulations. So that is where we see accelerated computing with GPUs playing a key role in enabling designers and engineers to be able to do these higher fidelity simulations faster. So if you go to the next slide, Jim, yeah. So I mentioned, how the GPU compute is scaling. If you see this chart, it has been growing. It has been scaling almost, linearly year over year over the past few years. Why GPUs are the game changer when it comes to simulations? It's because of the nature of its architecture, right? GPUs can have hundreds or thousands of cores that are doing these calculations. Many of these calculations, especially when it comes to CFD and electromagnetics and such, they are a lot more efficient as they can do thousands of these calculations, millions of these calculations in parallel. And another factor is the memory bandwidth. The memory bandwidth is doubling, tripling for these GPUs with every new architecture that we are coming out with, and that enables these simulations to be done much faster, as we will see in some of the benchmark slides later. As compared to CPUs, right? CPUs have a fewer number of cores. The calculations are not done in parallel essentially, and the bandwidth can be a bit of a limitation. CPUs are still required, right? CPUs are working in conjunction with the GPUs. But in many of these simulations, in many of these solvers, the compute is essentially offloaded to the GPU, while the CPU is doing other operations to make sure that all of these GPUs are getting all of the data for doing these calculations, and that's how overall we are speeding up these simulations. If we go to the next slide, Jim. So the way we see this developing is, majority of these simulations, if you go back, let's say 15 years or so, majority of these simulations were all CPU based, all simulation applications, ANSYS, even other ISVs had CPU based solvers. But we have been working with these ISVs over the last 2 decades or so, helping their developers port these solvers to the GPUs, and the result is that we are in the transition phase from CPU compute to GPU compute, computing on these accelerated platforms. And what this enables designers, engineers, simulation specialists to do is to run larger models, right? You can add more model, as Jim mentioned earlier, while getting the results much faster. The accuracy is the same. There have been many benchmarks. Even Ansys Fluent has a benchmark comparing CPU GPU results, and the results are identical. So you can run larger simulations, you can run them much faster, and you can perform more optimization studies to be able to make sure that you're delivering the best product that you can. So from this accelerated computing stage, where we are going next is, I'm sure you're aware of all the AI ML related discussions that are happening in terms of simulations, right? How AI can provide even earlier insights. Instead of running 10, 15, 20 high fidelity simulations, which can take longer, you can perform 1 or 2 higher fidelity simulations and use AI to get earlier insights, which will help you kind of maybe more design iterations, more optimizations. There are many benefits from it. So I think we are at the cusp of that, going from accelerated computing to incorporation of AI in these simulation workflows. And again, this is something that we work very closely with ANSYS in making sure that the ANSYS development team has the latest libraries and toolkits that NVIDIA develops to be able to accelerate these simulations. Let's go to the next step. So as I mentioned earlier, right, we have been working with the ANSYS team for almost 2 decades now, and it's not just the GPUs that are accelerating these simulations. It's a lot of these libraries and toolkits that ANSYS has incorporated in their various solvers. So for example, CUDA, CUDA is what enables these GPU solvers. So the Fluent GPU solver is based on the CUDA platform that NVIDIA develops. And that is really what makes these simulations much, much faster while running on GPUs. It's not just Fluent. ANSYS has a very broad portfolio of products, right? ANSYS has optical simulation applications such as SPIOS and other applications that are also, they also have GPU solvers. ANSYS Discovery has GPU solvers. HFSS and Lumerical on the electromagnetic side, they have GPU solvers. So you'll see more and more coming from ANSYS in the next few releases from their products. We will dig a little bit deeper into these performance numbers that Corey has run. But just to give you a very quick overview, right? The native GPU solver has shown astounding performance gains in ANSYS Fluent, right? The first few bars that you see here, they are CPU numbers. And then starting from L40 onwards that you see in the middle of this chart, L40 is the NVIDIA data center or the server GPU. And you can see how the performance scales linearly when you add more GPUs, typically 2, 4, 8. When you're doubling the GPUs, the performance almost doubles. And then we go to other GPUs like the A100, H100. The numbers there are again quite impressive. And really the choice of which GPU to use for your applications, for your simulations, it really depends on the form factor, right? As we will see later on, you can do a lot of these simulations on workstation GPUs like the 6000 series or the 5000 series. And if your simulations are really large, like external fluid dynamics and such, then the data center GPUs like the L40 or the H100 might be a better fit. But it really depends on your application, your model size, and such. Let's go to the next slide. Just a couple of customers who are now running all of their simulations, ANSYS Fluent simulations on NVIDIA GPUs. Leonardo Helicopters, when they are doing external aerodynamics for their helicopters, they are now running these simulations on NVIDIA GPUs. The ANSYS Fluent solver for a long time has been a hybrid solver. It was a CPU GPU solver. Some of the calculations were offloaded to the GPU and some were done by the CPU. But once they transitioned from that hybrid solver to the GPU native solver, they were able to cut down the overall time, and they were able to run many more simulations on their data sets. Next slide. Seagate, very well known in terms of memory and storage and other, components that go in data centers and computers. So they have been able to see a 50 times or a 50x improvement in their simulations of these hard drives and storage drives. And essentially, they're able to, evaluate more designs over a shorter period of time and helping them to come up with more optimum designs. So these are just two of the examples, but there are many, many customers who are now running their Fluent and other ANSYS simulations entirely on GPUs. Next slide. I think this is my last slide, Jim. So again, thank you all for joining today, and I am going to hand it over to Justin to talk about some of the ways you can access these GPUs for running your simulations. Thank you.
Thanks, Himanshu, for the introduction. Again, my name is Justin Wang. I'm the product marketing specialist at Exxact Corporation. You can go to the next slide, Jim. So we partnered with Fastway and NVIDIA and our partner with ANSYS as well to combine our expertise in delivering advanced computing hardware with a specialized expertise in simulation so that we can deliver you guys an optimized solution so that you can reduce your simulation time and meet the complex demands of engineering and simulating whatever you need to simulate across multiple industries, whether that's electronics, that's computational fluid dynamics, whether that's like fans or cars, whatever you're simulating, we want to provide a unique hardware experience for your specific workload. Go to the next slide. So I want to reiterate why you should choose GPU over a CPU, specifically for something like Fluent or the photonics type of research and simulation. So Himanshu touched upon this, and that CPUs handle tasks sequentially. So that's one after the other that result in those really long simulation times. They can take days, sometimes even like weeks if your model is really complex. Whereas GPUs, on the other hand, will utilize a parallel processing technique where multiple calculations are ran at the same time. So think of it like pixels on a screen for video games. When you are simulating those graphics, or you're running those graphics and rendering those graphics, they happen all at the same time so that you get a very pleasing visual image, especially in those really big AAA titles with numerous numbers of polygons. So in the same way, in a CFD simulation, you get all those elements and all those particles being simulated at the same time and calculated at the same time. That would result in a increase in complexity. Go back to the last slide, Jim. So the complexity means that you can increase the model size of your simulation, which allows you guys to retain your complexity and retain the information that you want to simulate and draw better conclusions before you start your prototyping process. And lastly is budget. So a single GPU node can have equivalent performance to hundreds and hundreds of CPU cores. And that can drastically not only reduce the number of servers or workstations you deploy, but also reduce the energy costs and opportunities for scale, because you can now deploy multi-GPU nodes instead. Go to the next slide. So we want to highlight our expertise in delivering the solutions for you guys. Exxact is a 30-year company that's been delivering high-performance computing solutions for a really long time now. And we help you evaluate, build, and integrate and optimize workstation, server, or cluster from start to finish. And we have numerous partnerships with multiple hardware partners. And we were actually named NVIDIA's 2024 Solutions Integration Partner of the Year. And we were recognized for our expertise in architecting and installing systems that tackle AI, manufacturing, simulation, life science research, and as well as other industries as well. We understand that every workload is unique, whether you're doing multiple softwares, whether you're solving on Fluent one day and mechanical or Dyna on another day. So we want to make sure our solutions are flexible to your every need, whether that's you need more GPUs, more CPUs, we're here to help. So our end-to-end services, they're all built to order, stress tested and validated to make sure that you can have a day one operational system. You can go to the next slide. So we have a couple of solutions here that I just wanted to highlight. So you can always start off with an individual workstation on the left-hand side, which could be a normal Core i9 with multiple high-performance GPUs. And that would be more centered towards the CFD side, where you're only doing more the GPU-heavy things. Or you can go with a dual Xeon quad GPU rack-mountable workstation, which could also act as a server in your rack. And this can be outfitted with a more CPU and GPU balanced system. Now, if you scan that QR code, you can go ahead and see a bunch of our other systems that you can configure, which include servers, so 2U servers, 4U servers. And if you are interested, you can also talk to our team about deploying a multi-GPU cluster, and we're capable of setting up and configuring a system for you to run really, really complex simulations to drive your innovation. All right, and that's all from me. You guys can, again, you can scan that QR code, and I'll drop a link in the chat for you guys to check out. And yeah, that's all for me. I'll pass it back to Jim.
Awesome. Thank you guys so much for that. You know, it's really fascinating to see all the development work that NVIDIA is doing. And just to reiterate, this is explicitly developing software and hardware alongside each other so that Fluent can take advantage of CUDA cores, and that for the foreseeable future, there is a scalable solution, right? Not everyone invests in hardware every single year. Usually it's a couple years at least. And so we really appreciate the partnership from Himanshu and Justin so that we can help our customers and help our friends and colleagues who are in the industry on how to develop a strategy for growth on the simulation side, right? So that brings us back to the model. I want to share with you just a few slides on what Corey has done over the last about several months, and to sort of flex, for lack of a better word, some of the high aspect ratio fine details. So this model Corey created, as you will probably recognize, looks a lot like a workstation with a consumer grade or even higher GPU in it. And what we focused on was a really, really high number of small geometry features. And particularly back to the original point around porous media assumptions and sort of tricks of the trade, if you will, in CFD, we have no tricks here. This is a full fidelity model. So there are over 3,000 openings, 3,000 inlets, outlets, and passages between the two fans in the front and the outlet grates, if you will, in the machine, as well as that GPU is boxed in and has its own sort of openings in it. And we really wanted to push the cell count up, as well as push the GPU up. But this isn't the largest model in the world, right? You've probably seen some meshes and some CFD benchmarks. In fact, Himanshu had one on earlier that was quite a bit larger than this, the Drive Air external aerodynamic model, which is tested very, very commonly for GPUs. This is 17 million, okay? And we actually polled our customers to find out what a typical cell count is for a workstation, or let's call it an engineering challenge. And what we found out was it's somewhere in the 10 to 20 million cell range. So historically, whatever hardware you had, you're targeting some ceiling, because anything higher than that, maybe you don't have enough RAM or it takes too long. So Corey built this model out. You can see the level of detail, right? So in the top upper right-hand corner in the middle, you can see we've got some industry best practices for boundary layer refinement. So several inflated layers, if you will, up on the wall. We've got, gosh, I don't know, 10 or so elements through the thickness in between the fins on each of the heat sinks. So really trying to capture the true thermal and fluid boundary layers so that we can capture the most accurate heat transfer possible. That only took about 7 minutes on meshing, so not too bad. And we were using the latest Fluent watertight workflow, what we call polyhex core. So you'll notice we've got beautiful, perfect hexahedrals in the free stream, but as we get up towards the wall, we've got some polyhedra and some inflated layers. Okay, so Himanshu mentioned earlier on the accuracy side, okay? And anyone who runs CFD knows that you can run the same exact model twice and it won't give you the same number, but the differences are probably past the decimal, and that is true in this case as well. When we compare the results of a transient CFD on the GPU versus the CPU, you don't have to worry about measurable differences in the predicted temperature. In this case, it is 0.2 degrees Celsius. So as you start to think about doing benchmarking of your own, you can trust that the results, fluids, velocities, pressures, temperatures, what you're used to on the CPU side, you're going to still get that on the GPU side. Of course, it'll be a little bit quicker. So you can see here the number is pretty close, and the thermal profile on the boards is almost identical. There's always going to be some nuances, right, because of the fluid flow being very dynamic. So let's move on to the results of the benchmarking. So first things first is our standard benchmark. So the CPU machine that we have, which is kind of a daily driver, so to speak, is a 32 core machine that we use 30 cores of. That's sort of the results of getting the most out of that machine. And so that's got 256 gigs of RAM. And we ran, Corey ran, some steady states and transients, because we wanted to just kind of compare different, on the engineering side, maybe some of the convergences and some of the iterations, and we try to normalize that. But we did test a steady state analysis and a transient analysis across the board, sort of a heads up. And so on the overall speed up, that's what we call sort of a 1, if you will. But just so that you know, the transient model on that 30 core machine did take about 2 weeks, right? 16 plus days to get the transient, and I won't go into the physics of what was transient and what wasn't, but to get that to converge took 16 days. That is pretty much a non-starter with respect to, is this a simulation that I can use as an engineer to make some insightful decisions, right? I don't want to wait 2 weeks for an answer. And that's even at 14 seconds per iteration. But again, at a transient, sometimes we have the time steps pretty low, and we need to get some high fidelity there. So the first thing we compared that against was the RTX A6000. And so just a single A6000, which, by the way, is just slides into the slot that's in the same machine as that benchmark machine. So all we're doing is using the same box. Everything's the same. We're just using the GPU that's in there instead of the cores, the CPU. The starting point was a 9x speed up. So we're basically at 10x, and all we did was use a single A6000 in that machine. And of course, with a properly designed machine, we can have the ability to slide in a second or even a third and fourth. And so when we compare those together, we see even more speed ups. As Himanshu was showing earlier, we see a lot of linearity with that as well. But ultimately, if you were to invest on a 6,000 platform and fit a quad setup in there, you're looking at a 25x speed up, 23 and change. That's a 23x speed up on 30 cores. So if you were on 4 cores today, and there are a handful of people who are on the 4-core setup sort of out of the box, now you're talking about 100x speed up. So as you look at where do you want to invest hardware, you have to be looking at GPUs. And it just gets more interesting from there. So going to the Ada platform, right? We've got the 4500, which has 24 gigs of RAM, the 5000, which has 32 gigs of RAM, and the 6000, which has 48 gigs of RAM. And so judging on the model size and how much RAM you need, you could see upwards of 20 to 30x speed up, depending on how many GPUs you have. And that is all in a workstation. So you can have it underneath your desk, and it's insane how much you can get. You really can't get that speed up on a CPU setup in a workstation. You can't. You already have to go to the server, which when you go to the server, for example, we've got the L40S here, you just have a lot of extra overhead, right? You've got the IT overhead, you've got the power overhead, you've got the noise overhead, because usually the fans on those machines are very loud. But if you've got the infrastructure and you want to just go for the moon, an 8 L40S is a 70x speed up over 30 cores. So that's just absolutely incredible. That transient model, by the way, if it was originally 16 days to solve, if you went full systems go, the L40S setup with 8 of them, we're talking about going from 16 days to 6 hours. So now that becomes a model that you can use as an engineer, because you can set it up in the morning, you can look at your answers before you go home, you can set up a new model, and you can solve it overnight. So you're doing 2 iterations a day, possibly more. If you're a workaholic like some of us, you might be able to squeeze in a 3rd iteration. And that now becomes a usable simulation. You don't have to simplify it. You don't have to introduce all the other error like you do sometimes with porous media assumptions. So that's the results of the benchmarking that Corey was doing on the model. If we were to look at that in a slightly different way, we have a nice sort of graph here, and you can see just how much that speed up is. And again, the RTX series are all workstation-based GPUs. And even if you didn't have a budget, say for 4 times the 6,000 ADA, you could get one. And that's a platform you can invest in over the next several years, right? Because you can put a second one in next year, and they're just going to get a little bit cheaper as time goes on. And then a couple years later, you can put two more in, and you're going to still see a 17 to 24 to 30x speed up on that particular machine. So that's pretty incredible stuff. To be honest, to be perfectly candid, last year when we were preparing for this benchmark, we were a little, we'd seen the white papers, we'd seen the PDFs, and we're like, yeah, we'll see how that goes. Those are all, 100 million cell models. We want to see how it works on something a little more realistic for what we work on and for what our customers work on. But we're still seeing, 10, 20, 30, 40, 50x speed up. So pretty incredible stuff. With that, I'm gonna pause for a second, and I'm gonna open up to Q&A. If anyone has any questions, feel free to. I think you can unmute yourself on the mic and ask a question. We've got Himanshu and Justin here, as well as myself and Corey, and feel free to fire away, or you can type it in the chat as well. No questions at all.
So I had a question about what is this looks like the L4 OS. Yeah.
Yeah, the L40S, yeah.
Yeah, so is this something that's, already commercially available, like on the market for NVIDIA, or is this something that's still in development?
The L40S is an available card. It's from the ADA generation, which was released, I believe, 2 years ago. I believe NVIDIA is in the process of releasing the Blackwell versions, so those will be coming, I believe, this year or next year.
Thank
Yeah,
you.
but
all
just
these
to answer,
cards are available.
reiterate what Justin said. The L40S is currently available. It is a server or a data center GPU.
Yeah, I think that's a great question. We wanted to test available cards. So everything you see here, these are, you can go right on to, I've got the link, and I think looks like Justin put the link in the chat as well. But if you want to build your own machine, that's at a unique landing page that we have built with Exxact, so that you can see that these are the ANSYS certified, ANSYS optimized machines. One of those machines is the exact machine that we were testing on. So this is totally obtainable.
In fact, just to add to that, all the GPUs that are mentioned here, workstation GPUs and data center GPUs, except the A6000. The A6000 is the previous generation of GPUs. When you see, 4500 ADA, 5000 ADA, 6000 ADA, L40S, these are all the current generation GPUs available from our partners like Exxact.
Thank you.
Yeah, you're welcome. Looks like we've got a question. Can we comment on the cost difference between the 30-core AMD workstation and any of the other workstations? We're not really prepared to talk about cost on the presentation. Certainly we can follow up. I don't even know, I don't remember the cost of the 32-core build that we put together there. It's been a number of years. It was actually a one that we built on our own. So we put it together. Corey and I put it together, and it's been our workhorse for CFD ever since. As far as pricing for the GPUs that we show here, all of that is right now available on Exxact's website. So you can get ballpark pricing per GPU, per build, and that's the quickest, easiest way to get numbers. But I would generally say that the 30 core, we say it's a 30 core because we use 30, but the machine itself has 32. That is just a typical workstation build, and it was about half the price if you were to go and just get a warranted, name brand OEM. Like I said, our workstation for CFD is something that we built ourselves, but it's nothing special. It's something that anyone can put together. I mean, even the 32 cores from AMD nowadays is not even close to the 64 and the 128 dual sockets that are available for engineers now. Great question from Nitin, who is asking, how can reduced order models be utilized with GPUs? So that's a great question. So let's say, for example, for those who don't know what a reduced order model is, let's say I have to build a 17 million cell CFD model, and I have to enter in all the inputs and wait, whether it's a few days or a few weeks or a few minutes for a solution. We're really solving 17 million times the number of variables in the equation. So that can be a heavy lift. And as we look at ML and AI applications, right, and we wrap around, say, intelligence or predictive algorithms around the core physics, what we do is we take the core physics, a 10, 20, 100 million cell model, and we reduce that down to maybe half a dozen at most, maybe a dozen degrees of freedom. And we call that a ROM or a reduced order model. And that's used to build out large, say, design of experiments. So a great question, Nitin. How we would use that with GPUs is there's a variety of software that we have in Ansys that would, if you will, wrap around and get hooked in to our physics solvers. But all of that can be used on any of the machines that you see here. So if I wanted to use a GPU to create, say, several large scale models, I would use that as, say, training data, if you don't mind if I use that term, to make my algorithms a little bit smarter. So I can't comment right now on whether or not the software that we use to break it and develop an ROM is available on GPU. I don't know off the top of my head. I can get back to you on that. But certainly, if somebody were to develop a predictive model, you're going to need a combination of software and hardware to do that. And to make it smart, to make these predictive models actually predict something with a high level of confidence, we need good training data. The training data doesn't come from reduced order models. The training data comes from full physics. So no porous media, no Darcy's Law, mesh everything, crank up the mesh, crank up the cell count, put it on an NVIDIA GPU and accelerate it.
Yeah, I will add to that, Jim. Thank you for that answer. Sim AI is an application that Ansys announced and launched maybe, I don't know, sometime last year, and that is one of the applications that helps you run these reduced order models and such. And like Jim mentioned, it relies on your existing simulation data. So, the past simulations that you have run, you can use those to train the model. And then, the next simulations that you're running, if there are some minor design variations and such, they would run much, much faster based on the AI, the training that you have given to the model. And Sim AI is something that we have worked with Ansys in creating that. Again, there are some NVIDIA libraries and toolkits that are in use there, and it is also GPU accelerated, so you will get much faster results that way. A second second possible solution, if you want to do some of that on your own, right? You have a lot of simulation data, simulation results, and you want to do the model training yourself and run these type of simulations. NVIDIA provides a framework called Modulus. I will drop a link in the chat here. But using the NVIDIA Modulus framework, you can train your own models with your simulation data and then, run these reduced order models, again, where GPUs will give you excellent performance.
Awesome. Yeah. I'm glad you mentioned SimAI, Himanshu. I wasn't going to mention it quite yet. I know we're really excited to see where that tool goes, but it's really exciting to see the convergence on where a lot of the software and hardware is going. We've got a great question here from Z. For L40S, is there a cloud service that would allow for pay-per-time usage? So I don't know. Exxact, I don't know, Justin, if you guys offer that service, or would it be Himanshu if you've got something?
Yeah, so Exxact is an on-prem focused solutions integrator, and we would recommend that if you were to run simulations and you're running them for a very long time, cloud services can drastically add up as you keep using them. So if you were to run multiple iterations on a model using an L40S or using a server or any GPU in that matter, multiple simulations running at like 6 hours, for example, for this example, would run you a lot of money as you keep ramping up and you keep continuing to use. So an on-prem solution would be a good idea if you were to invest in your workflow. But if cloud has that advantage of a lower barrier to entry, so you just have to ask around your cloud providers to see what kinds of GPUs they offer.
Great. Awesome. Thank you. It looks like Himanshu just put in a link to the neural network framework from NVIDIA into the chat. So we're kind of running out of time. I just wanted to ask if anyone's got any more questions. Otherwise, we're going to stop the recording. We'll end the webinar, and we look forward to connecting with everybody, whether it's on LinkedIn or through email, and continuing the conversations around accelerating and entering insight using NVIDIA computing technology. So with that, I want to give a huge thank you to Corey for the heavy lifting here, for Himanshu, and to Justin and to your teams for letting us put this data together and gain access to the technologies and share it today. So thank you guys for joining us. If there's any more questions, fire away. Otherwise, have a great rest of your day.